Good afternoon, everybody, and welcome. Just wondering, since we have a good crowd this afternoon for today's talk, any first-time visitors to the SETI Talks series? A number of you. So a very special welcome to you. It's great to see new faces here for our colloquium series, which, if you don't know, we do every Tuesday here at Microsoft. No, not last. No, last we had unfortunately we had a cancellation due to an illness of the speaker. But normally we try every Tuesday to have the session here at Microsoft, and we love to welcome new visitors. For those of you who are new to this series, you can pre-register for the talks. It is not required by any means, but it just makes things a little easier. When you pre-register for the talks, they do up one of these badges for you that are then waiting at the front desk downstairs. They should. Okay, we've been, yeah, they're normally there. If yours hasn't been there, we'll. Okay. All right. Well, there's several. Yours may be there. Okay. Well, we'll take care of yours for sure. Yeah, there you go. And if you do get them, because this also helps, just hold on to it because it's good every time. And then the next time you come to the talk, you can just cruise right past the front desk downstairs. They'll buzz you in, and you can come up. So again, a very special and warm welcome to those of you who are here for the first time. And before we get into today's talk, I would like to tell you that we're going to have a commercial interruption before we get started. And that's to let you know that at this time of year, not surprisingly, we've just embarked on our year-end fundraising campaign for the SETI Institute. We've kicked that off with a short little video clip that went out to a lot of our followers via email today. So we're going to show you that clip. It's just a little bit over a minute long, and tell you a few more things about it, and then I'll introduce today's speaker. Hi, I'm Bill Diamond, President and CEO of the SETI Institute. 2016 has been another exciting year of exploration and discovery here at the Institute. The Kepler mission, including a dozen of our research scientists, continues to find hundreds more planets orbiting distant stars. Many of those planets are in the habitable zone, possibly supporting liquid water and thus the prospect of life. During the year, we turned the Allen Telescope Array to Tabby Star, one of the Kepler planetary systems whose light curve continues to mystify astronomers and astrophysicists alike. Some have even proposed that only an alien megastructure could explain such a strange phenomena. The Kepler mission has had a profound impact on our understanding of the universe and our place in it. We now know that planets are everywhere. So take note, when you look up at the night sky, it's a pretty good bet that every star you see has one or more planets orbiting around it. And there may be somebody like you, or perhaps very different from you, looking up at their night sky and also wondering, are we alone? Our research involves NASA missions like Hubble, New Horizons, Cassini, and Kepler. It takes us across the globe, to the frozen lakes of the Antarctic, to the ancient craters above the Arctic Circle, and to the dry desert of the Atacama, to name but a few. To continue our research, education, and outreach programs, we're looking for your help as we embark on our year-end campaign. Your support is urgently needed and very much appreciated. Thank you. So thank you for listening to that. The reason we did that as a video is if I had to memorize that and do it again, I'd completely mess it up. So I appreciate your patience in working through it. But it's a very serious endeavor at the Institute. Much of the work that we do relies on support from friends and donors. Basically, all of the SETI, the actual SETI research that we do that is not funded by NASA. This involves the use of radio telescopes, including our own Allen Telescope Array, optical SETI programs, our outreach activities, including this colloquium series, our big picture science radio program, our website and social media in which we fill the content there with information about our science and the science of our colleagues at institutions across the US and also colleagues at NASA. So all of those programs require philanthropic support in order to work and to be delivered. And our goal this year is to raise about $1.3 million in the new fiscal year, which started October 1st of this year and ends September 30th of next year. So we'd very much appreciate any consideration, however large or small, that you're willing to make. If you would like to support the work we do, It's very easy. You can go to our website, which is SETI.org, and there's a donate button there, and you can very easily make a gift or donation. And I'd also like to once again thank and recognize Leonard Tremmel for his sponsorship of this colloquium series for this past year. So it's thanks to Leonard's generosity that we've been able to put that on. So anybody else willing to stand up and be next year's Leonard, please let us know. But we're very grateful for his support and for all the support from those of you who help us through the year. So with that, let me get on to introducing today's speaker. And we have a grand topic today, about as large a scale topic as one can discuss in any sphere of any kind. So we're very excited to have this talk. I prepared a couple of notes of this because I have actually even a personal history here that goes back to the 1980s. So in that big picture realm of astronomy known as cosmology, and not to be confused with cosmetology, the organization of structure arguably begins at the stellar level, though most cosmologists rarely address astrophysics on that scale. Stars are organized into galaxies, which in turn form galaxy groups, galaxy clusters, superclusters, sheets, walls, and filaments, which are separated into immense voids, creating a vast foam-like or soap bubble-like structure, sometimes called the cosmic web. But really, much before 1989, it was commonly assumed that virialized galaxy clusters were the largest structures in existence, and that they were distributed more or less uniformly throughout the universe in every direction. However, since the early 80s, more and more structures have been discovered, and we now know that there are grand schemes and grand structural scales we're only beginning to understand. I remember very distinctly in 1989, my mother telling me about the work of Margaret Geller from Harvard-Smithsonian. My mother was an art historian, so didn't really follow the world of astronomy and cosmology all that much, except having a son who was a physicist. She loved to follow the news and stay on top of it. And she was delighted to tell me that both there was structure in the larger scale universe and also that it had been discovered by a woman. And so I will never forget that conversation and how much fun it was, but also how interesting and intriguing it was. So in 1989, Margaret Geller and John Huchra discovered the Great Wall, a sheet of galaxies more than 500 million light years long, 200 million wide, but only 15 million light years thick. The existence of this structure escaped notice for so long because it requires locating the position of galaxies in 3 dimensions, which involves combining location information about the galaxies with distance information from redshifts. So today, I'm very pleased to introduce Mehmet Alpaslan, who received his PhD in astrophysics from the University of St. Andrews School in Scotland after spending 2 years of his doctoral studies at the University of Western Australia. His dissertation focused on studying the large-scale structure of the universe with galaxy survey data, which is largely what he continues to focus on today. He also completed his undergraduate studies at the University of St. Andrews, where he completed a 5-year integrated master's program, overall earning himself the full title of Master's in Physics with honors in astrophysics. Mehmet's now working at NASA, where he's a postdoctoral fellow. His work at NASA focuses on studying the environmental dependency of galaxy evolution. He primarily works with data from the Galaxy and Mass Assembly, or GAMA, survey, and tries to understand a galaxy's position along the cosmic web influences its observable properties, and how the cosmic web influence its observable properties. This research is in alignment with NASA's Physics of the Cosmos and Cosmic Origins program, which aim to understand the formation history of the universe and its constituent parts, including galaxies. It is this work that he will be discussing during today's talk. And I do want to tell you that his early inspiration was that well-known book for many of us in the audience today, Cosmos, written by Carl Sagan. And he told me the story of coming across that book as a 15-year-old on his way to Chile, where he was fortunate enough to spend some time and see some of the observatories there, and where I just came back from, having been with our NAI team there. So another inspired astronomer from Carl Sagan. And so it is my great pleasure to introduce Mehmet to you and to look forward to your talk.
Thank you very much. So I was under the impression that there was a clicker. I think it's maybe this one.
Oh, yep, there it is. Okay, perfect. Well, thank you for the wonderful introduction and also for the great summary of the topic today. That actually saves me quite a lot of work. I appreciate it. Thank you all for coming. So, as was mentioned, I'm currently working as a postdoctoral fellow at NASA's Ames Research Center, and the research that I'd like to tell you about today consists of a lot of work that I've been doing over the last few years, and I'm currently doing at Ames. So, the talk of the title is essentially talks about how galaxies are influenced by the largest scale structures in the universe. But I'll begin first by telling you a little bit about the kinds of structures that we look at, try to give you an understanding for the kinds of scales that we're observing, and also go into some detail about actually how we gather this data. Because it is my opinion that sometimes talks about the subject don't necessarily go into enough detail about how astronomers go about the process of gathering this data from telescopes around the world, and I think it's a fascinating endeavor. That'll consist largely of the first half of the talk, after which I'll go into some detail about some of the algorithmic work that I've done in order to classify these structures that Bill talked about, these filaments and clusters and voids. So that'll go into a little bit about some of the computer science work that goes into this. And I'll finally end by talking about some recent results that we've had over at Ames in this work. So, just to start off with, I want to tell you about the kinds of, let's see if this works. No, I guess not. Okay, I'll just come back to here. So normally with these kinds of things, it's very difficult to explain the scales that we look at with mere words or numbers or pictures. A video is really what's necessary. And so I'll begin by showing you this video by the American Museum of Natural History entitled The Known Universe. And the key thing about this video is that, as the text will explain in a minute, everything that you're going to see is based on real data. So this was made back in 2005, and the positions of all the stars, all the planets, even the satellites, and towards the end, the galaxies that you will see are based on real data. None of this is artificial. It's all to scale, and what it will do is start here in the Himalayas in Tibet and gradually begin to zoom out. Oh, and we have audio, but I'll mute it for now. So you can actually go and view this on YouTube and listen to the soothing music that goes along with it. This, to me, is a mesmerizing video, and as you'll hopefully agree, it will do a very good job of explaining exactly the kinds of scales that I begin to work at. So we've got satellite imagery now, and it's beginning to zoom out from Earth. And remember, the background stars that you see are all real structures, real positions that correspond to their actual physical locations. Here, of course, is the beautiful planet that we see, and I believe even the cloud coverage is accurate for that time. And we'll now begin to rotate around the Earth, despite what the Flat Earth Society might try and tell you. It is, in fact, a sphere, despite their best attempts. Orion there just tucked in behind, and now we can see the positions of satellites and their orbits. This was back in 2005. I'm sure this has only increased since then. And of course, most of these are telecommunication satellites, as well as some other scientific instruments. One of the striking things to me just this early on is just how close in these satellite orbits are to the Earth. This is something that doesn't, at least to me, it's not something I think about until the video will zoom out a little bit more and show you the orbit of the moon. But really, we've only just explored a tiny fraction of space, and I find that fascinating. So let's zoom out, and very soon now we'll begin to see the orbit of the moon. I want you to keep an eye out down there at the bottom. It'll show you at regular intervals the amount of time light takes to travel out to these distances. So now we'll begin to see the orbits of the terrestrial planets of the inner solar system. So, of course, Mars, Venus, Mercury. And we'll begin to zoom out past the asteroid belt to the gas giants. And now we're 1 light hour away from Earth. And things are going to start picking up here now. So I'll try and speed up. We're at 1 light day away from the universe. And now you can see the zodiacal constellations in the background. But I want you to keep your eye on those, because you'll begin to see those familiar patterns begin to distort as we move so far out that the positions of those stars are no longer in their relative positions as we see them. Of course, now each of these points is an individual star. We're about 70 light years away from Earth, and this is now humanity's first radio signals. These have had the time to travel out from the Earth. And now, of course, we see our galaxy, the Milky Way, and you can see that we're sort of in the boondocks of the galaxy towards the edge. Here's where my work kicks in. Each of these individual points is a galaxy. And this is data that we gather from what are called galaxy surveys. This is where you take a telescope and you map out as much of the universe as you can. Again, each of these points is a galaxy. This is mind-boggling stuff. I'll tell you about why we care about all of this, but personally, this is just very cool. That's why I do this. I mean, I have to write down that there's important scientific applications. And of course there are, but to me this is fascinating. Here at the outer edge, we've got quasars, which are these superluminous objects that we map out with surveys such as BOSS and eBOSS. And at the end of it all, of course, is the cosmic microwave background radiation that represents the furthest that we can see before essentially physics blocks us out. And the video will begin to zoom back in now. And remember, the key thing here is that each of these points are galaxies. And this shows you the kind of wealth of data that we have on hand now to study the properties of this cosmic web, which you may have seen is characterized by these large filaments that connect these clusters and surround voids. And I'll have static images of these later to show you. Now, as the video zooms back in, I'll give you a bit of a preamble to the next video that I'm going to show, which will be a simulation of how these structures originally formed. This was some of the earlier work that went into this particular field of this large-scale structure, in understanding just exactly how these structures form. And nowadays, we understand it reasonably well. If you have a box of particles in a simulation, for example, that you let evolve simply through the interaction of gravity, while also injecting some more complicated physics such as dark matter, or if you like, an alternative theory for gravity, you can reproduce the structure very, very well. So shortly after the Big Bang, you have this essentially a sea of matter, which is slightly more dense in certain regions and slightly less dense in other regions. I kind of liken it to a minestrone. You know, you've got the thick, chunky vegetables in one part and just the broth in the other. So gravity works by density. The more dense a region is, the more gravitational attraction it will have. And what you'll see in the next video shortly is that these more dense regions will accumulate more matter simply because they have more gravitational potential from the less dense regions. And that will give rise to this pattern of cosmic filaments and voids. So I'll save you the ending of the video. It's just going to zoom back in. You can go and watch this for yourself. It's a fascinating video, and the music is very nice. And you know, I hope they release an updated version soon to reflect the amount of information that we've added to this figure. So these are two simulation boxes that I've told you about side by side. These are both the same simulation, and they'll run concurrently. The one here on the left will show you a static image, while the other will rotate around the box, so you can get a feel for the three-dimensional distribution of points. This number on the top left represents the redshift. You can think of this as time, essentially. Redshift 0 corresponds to the present day, and the higher the redshift value is, the further back in time you're looking. So let's get the video started. And you'll see that even though that initial distribution of points looks uniform, these accumulations of density, these regions that are more dense, will immediately begin to form more structure. Now, the simulation doesn't run exactly to redshift 0 or to the present day, but it certainly goes in close enough that you can see this familiar structure pop up. What I'd like to draw your attention to is the formation of these filament-like structures. This is really where you see these density fields collapsing in on themselves and overlapping on top of each other to form these coherent structures. And you can see this all happening. And these are the constituent parts of the cosmic web. You have these clusters, you have the filaments that connect them, all of which surround these empty voids. Now, these simulations are of particular interest to people who are studying different models of cosmology. As I said, you can vary the simulation to inject a different model of dark matter. So for example, you can change the temperature of dark matter. You can add different physics to how gravity interacts with each other. But to first order, the model of cold dark matter, or lambda CDM as we call it, has done a fantastic job in being able to reproduce this structure. So at the very large scales, at these scales, we understand the physics of the formation of these structures very well, and also the kinds of dark matter and cosmology that form them. Here is a more detailed video. So again, this will show, the frame number will just count up, and then this will show sort of time. This isn't counting back now. This is just time since the beginning in mega years, or millions of years. So we'll see this gas cloud now beginning to collapse, and you'll begin to see stars forming. And eventually the stars will form and the filaments will take shape. And this video will tell you a little bit more about the kinds of physical processes that occur within these filaments to form galaxies and the objects that we see in the night sky. Now, one striking thing that should immediately jump out to you is that filaments are very busy places. Galaxies and filaments are in very dense environments. By virtue of having many neighbors, they're undergoing many dynamical interactions. And we know that dynamical interactions have great impact on the life cycle of a galaxy. The video is going to zoom in here to the central cluster of galaxies, and perhaps those of you towards the front might have an easier time seeing this. You'll see sheets of gas being expelled from the galaxy as more galaxies fall into it. This is one of the reasons why in clusters we observe galaxies that are typically bereft of gas. We call them red and dead. They're no longer forming stars. They're just these old populations of galaxies. This video is also on YouTube. It's by Feng Yu, so if you want to go back through and see it, I would recommend doing so. So you see these jets of gas that are coming out. So this highlights why I'm personally interested in studying this large-scale structure, because galaxies in different regions of the cosmic web experience drastically different dynamical interactions. It's clear here that a galaxy that's evolving in this kind of an environment will experience different kinds of interactions. So there'll be fewer galaxy-galaxy collisions to galaxies and voids. And there's clearly some difference in terms of what happens to the gas that inhabits these central galaxies. So the simulation is no longer moving forward in time, but it's simply zooming out, and it will eventually give you an overview of sort of the present state of this. So just to summarize, we can see from simulations that galaxies in clusters and filaments experience a more violent upbringing, so to speak. And we're interested in finding out if this difference in evolution history has any impact on the properties of the galaxy. And so there, the video is ended. Now, I've showed you all these sophisticated simulations, these wonderful pictures of how it all works. Things are slightly different in the observable world of observers. Here was the first one of these such maps. So this was a paper from 1986, which became famous for this stick man that was observed in the distribution of galaxies. Let me take a moment to explain what you're looking at here. I'll show a number of these sort of cone plots throughout the talk, so it's helpful to get a feeling for what they show. Each point here is a galaxy, and they're plotted according to two coordinates. Along the top here is the galaxy's right ascension, or if you will, just how far to the left or to the right you need to look in the night sky to see it. And along the central axis is the distance, which in this case is represented by its recession speed, which is simply the velocity at which it's moving away from us because of the expansion of the universe. And this can be converted into a physical distance. So the third dimension is sort of along the line of sight, and this is the declination, or just simply how high up in the sky the galaxy is, and that tends to get collapsed. And of course, here we are in the middle of it all, observing out into space. And so this garnered a lot of attention when it was first published because of this asterism that's in the middle. However, one other reason I like to show it is because it represents sort of the technical advancements that we've had in being able to accumulate this data. It took months to observe all of these galaxies, and I believe there's less than 2,000 points here. These days, that's small potatoes, if you will. Here's how it all compares to, and this is a slice of the universe from the Sloan Digital Sky Survey from a few years ago. Again, showing you the same kind of information, right ascension along the sides here, and then redshift along the radius. And these pie slices that are missing are simply regions that we can't see through the Milky Way because of the dust lanes in the core of the galaxy. The color coding here represents the number of galaxies along the line of sight, so along this density. And this structure here is the Sloan Great Wall that Bill was talking about, this massive superstructure of galaxies. So this is the cosmic web. These clusters that are connected to other clusters via filaments that surround empty voids. And so the question that I look at is a galaxy that's in this region systematically different to a galaxy that's in this region? And if so, why? And if not, also, why? So how do we actually get this information? And I was speaking to a gentleman before the talk began about how this information is actually gathered. It's very easy to pinpoint the position in the sky, sort of its right ascension and declination for a galaxy. But what's more challenging is the distance. And the real logistical problem here is essentially being able to observe as many galaxies as possible in order to be able to accurately determine what's going on. Because in astronomy, you can't conduct an experiment. You can't have something in a lab that reoccurs a number of times, and so you have repeated observations to hone your statistics. Instead, you just need to observe a large number of objects and be able to do large number of statistics from there. And so that's where new telescope facilities begin to come into play. So I'll show you a few videos. This one's produced by the Australian Astronomical Observatory, and this actually shows the telescope that we used in the Galaxy and Mass Assembly Survey to identify galaxies. So this is a 2-degree magnetic plate that sits on the focus of the telescope, which will be shown in a minute. And what's actually happening is this robot is moving to the periphery of this plate, picking up individual crystals that are connected to fiber optic cables, and placing them on the magnetic plate to an accuracy of a couple microns. And their position corresponds exactly to where the galaxies are once you point this magnetic plate onto the sky. And so this allows us to observe 400 galaxies simultaneously, or rather, light from 400 galaxies enters the telescope at the same time. Meanwhile, the drum rotates, and the robot is actually back here now, and it's positioning the fibers at the same time as the observations are being done. This is drastically sped up. It actually takes about an hour for this to happen. So this telescope is the Anglo-Australian telescope located in the southeastern part of Australia. I spent a good 35 nights here using this telescope with our team. And one of the things you'll notice if you're interested in this particular kind of stuff is that this dome is very large for a telescope this size. This is about a 4-meter telescope. And the dome here is colossal. And in fact, it actually sits on about 7 stories of office space so that it can be quite high up. This is a time lapse of the night sky. It's not actually this bright. This is just exposure adjusted to be able to show you what's going on. And so this is now showcasing an evening of observations of the telescope. But the key thing here is, again, you're able to observe 400 galaxies at the same time. And then you essentially rotate the drum, point it to a new field, and observe another 400. So in one night, on a good night, you can get close to 3,600 galaxies happening at once. So I won't wait till the end of this video. It's just going to show you more snapshots of the telescope. But it's a very beautiful location, and it's a place that I've enjoyed spending time at. Now, I mentioned that it takes about an hour for that configuration to happen. Newer technologies are actually speeding that up even more. And this is sort of the aside that I mentioned at the start. I wanted to tell you a little bit about some of the engineering that goes into these observations. So these are star bugs. These are actually fibers, again, that are connected to the plate. But what these will do, and this is a lot more apparent if you watch the video, is they vibrate along the glass to move themselves into the position, which you can see here. And so they're sort of coarsely positioning themselves at first. And if you have audio on this, it kind of sounds like one of those old disk drives reading data. It's fascinating to see. And these position themselves very, very slowly until they get to where they need to be. This takes significantly less time than the previous technique that I showed you. And this will actually be used by an upcoming survey called Taipan to, again, observe some of the galaxies in the nearby universe. And this actually comes to a position of about 10 nanometers, which is an order of magnitude of improvement to the microns that I was talking about earlier. So for the sake of brevity, I won't show you to the end of the video because these are sort of imperceptibly moving towards their final position. And again, yeah, it took only 42 seconds for that to happen. So that's a step up. Over here in the States, we have a slightly different technique where each fiber now is placed on 2 rotating engines. And so there can be sort of a coarse rotation here on the top end and then a finer rotation on the upper end. And this allows you to really accurately and finely position the fibers. The key thing here, again, is to be able to observe as many galaxies as possible. But another advantage of techniques such as this is that they allow you to place fibers that are very close to each other. So say, for example, you have a very crowded field of galaxies, where you have galaxies that are closer to each other than the maximum allowable distance between 2 fibers. If your technology allows you to place fibers very close to each other, then that means that you can observe that field in one single pass rather than having to revisit it multiple times with different fiber configurations. So I hope this aside was interesting in showing you that you don't necessarily have to be an astronomer to contribute to astronomy. The engineers have a lot to work on as well. And in fact, these are the kinds of rooms that they don't allow us into because of all the technical stuff that's going on. This is the spectrograph that lies at the bottom of the Anglo-Australian telescope that I showed you. And so the fiber optic cables come in and they feed that light into these 2 spectrographs, the blue end and the red end, which then tell you about the spectrum of light that's coming in. And again, yeah, I was not allowed into this room because apparently astronomers break things all the time. We have to sit in these dull old computer rooms that sort of, you just sit in front of the computer, and this control panel shows you the age of the telescope itself. But perhaps what's more interesting are the kangaroos that you get to interact with as you walk home at the end of an observing night, and then you get to go to sleep, thanks to helpful signs like this that make sure that tourists keep quiet during the day. So here is the present state of the universe in terms of how we've observed it. Each of these blobs, it looks like a blob, these are actually individual points that are plotted into the sphere, which shows the cosmic microwave background radiation again, and this look-back time, or distance. And these different blobs represent the efforts of different galaxy surveys in mapping out the universe. So the Sloan Digital Sky Survey is this vast green cloud. The survey that I work with, GAMA, has constructed these 3 equatorial cones that you see here and those 2 southern cones. So as you'll see some cone plots later on in the talk, these are the regions of space that I'm talking about. And to me, I think it's astonishing that we're able to map out this much. And I look forward to the day that we actually fill the sphere in. I don't even know when that will be. One of the interesting things is that you can actually, instead of observing further out, you can simply observe within the regions that we've already looked at. And rather than finding distant galaxies, you look for more faint galaxies, and you fill in that area of the parameter space. And finally, here is how it all comes together. This is a video produced by the International Center for Radio Astronomy Research and Durham University, and it's going to fly through one of the gamma cones that we've observed. So I show you this not because I'm sure you understand the point by now, but some of these galaxies are ones that I've mapped out personally, so I have an attachment to this video. So the images you see here are actually physical images of what the galaxies look like that have been scaled up to show their imaging. And so you can see this filamentary structure come in once again. The video is going to fly out and then eventually fly back in. So you have galaxies exhibiting different morphologies, different colors, living in different environments. And this is the key to what we're trying to study, is to understand how these different environments influence each other. And this video can be found on Vimeo. And so it'll hit the top there and then eventually fly back in. So we have imaging for these galaxies, but what did we spend 6 years at the Anglo-Australian telescope to get? We obtained spectra for these galaxies. And for those of you that aren't familiar with what a spectrum is, it essentially shows you the composition of light that you receive from a galaxy. And the composition of light will tell you about some of the emission features, so the kinds of chemical activities that are taking place in the galaxy. And so that can tell you about the formation of stars that are going on, the presence of nebulae that are absorbing light. And I will show you an example of this just as soon as this video ends, once it zooms back in. This is, to me, still mesmerizing. I've seen this video dozens of times. But I guess it's a good thing that I remain interested in it, right? So here's what a spectrum looks like. So on the x-axis here, you can see the wavelength of light. And then along the y-axis, the intensity of light that you receive. And this spectrum encodes a vast amount of information. The striking things are these spikes. So these are emission spikes. And what's happening here is that you have electrons that are around a nucleus being excited by light from stars that then jump back down to their original position and emit a photon of light at a very specific wavelength. So these emission features tell you a lot about the kind of star formation that's happening in the galaxy, or the amount of new stars that are being formed every year. Other kinds of spectra have these absorption features, for example, like these ones here, these dips, that tell you about some of the other kinds of molecular gas clouds that exist within the galaxy. Now, the physics of how these emission lines and absorption lines happen is very well understood. We can reproduce these kinds of jumps in the electrons of an atom in a laboratory. And so when you're doing it in a lab, you can say, okay, well, this physical process has this much energy associated with it. Therefore, the photon of light emitted from it corresponds to a certain value. However, when you receive that light from space, in the time it takes for that photon of light to travel to the Earth, space itself is stretching. And so you experience this process called redshift, wherein the wavelength of light that corresponds to this particular physical process is shifted backwards. And it's in this difference, for example, by measuring this emission line here and comparing it to where it would be if there was no such expansion, it's in this that you can compute a distance to the galaxies. And so here is what it all looks like when you build one of these gamma cones. So this is one of those equatorial cones that I was telling you about, again, viewed from ahead. So we have this distribution of galaxies, and this is where my work comes in. What I'm interested in is being able to say, statistically, which of these galaxies belongs to a cluster, which of these galaxies belongs to a filament, and which of them belongs to a void. Now, for you and I, this is very easy to do. I could give you a printout of this, and you could just take a crayon or a felt tip pen, and you could just draw on it. And chances are we'd roughly agree in terms of what we find. Telling a computer to do it, however, is a different undertaking entirely. And there's a whole cottage industry today dedicated to developing different algorithms that do this. It's a very active field and one that I'm personally very interested in. But the algorithms that exist fall roughly into two camps. The first are based on density fields. And so this is an example of a paper by Stoica et al. In 2008, where they take simulated data and they identify filaments using this density approach. What do I mean by that? You essentially take your distribution of points and you smooth it out. It's kind of like blurring an image. And you look at the gradient of how that density changes with position. So if you have a particular point where the density is at its highest point and it drops off in all directions, that tells you that you have a cluster, right? Because this cluster is this isolated dense structure with nothing big near it. On the other hand, if you have an underdense region, one where the density is minimum and it's increasing in all directions, that tells you that you're in the center of a void. Finally, lines that have essentially a constant density in one direction but drop off in another, you can kind of think of these as ridges, or the whole thing can be thought of as contours on a map. That tells you about where the filaments are. And so these algorithms are designed to join maxima in the density field through these linear structures, and they identify these clusters and lines very, very well. On the other hand, we have point processes, and these are more designed to work on observational data sets. And these typically rely on clustering algorithms to take galaxies, associate them with clusters, as was done in this paper by Murphy et al. In 2011, and then those groups of galaxies are themselves associated with each other through a second clustering algorithm to identify filaments. And these are color-coded here, so again, this is the Sloan Great Wall. So 2 different methods. I've shown you this point process method because that's the one that I've ended up using. And the particular mathematical technique that I use is known as a minimal spanning tree. And I suspect that this might be familiar to a number of you in the audience, given our geographical location. But minimal spanning trees are techniques used in graph theory. And graph theory essentially represents the relationship between different objects within a network. So this could be your friendship network. This could be, perhaps slightly more grim, it could be the network of infections for a given pandemic. This could represent the link that's infected other people. Or it could be a telephone network or anything like that. And so in graph theory, you can represent the links between these objects as these gray lines in the background. The minimal spanning tree, then, is simply the single continuous path that connects all of these points in the shortest possible distance. And this has a number of practical applications, for example, for the traveling salesman problem, right? Because you can determine where you want to go in the shortest possible distance and save fuel. In our case, it allows us to identify filaments because we're essentially identifying points that are close to each other and forming these filamentary networks that travel along them. Now, the nice thing about minimal spanning trees is that they're a very well understood problem. The algorithms that are used to determine minimal spanning trees were initially conceived in the 1930s, computerized in the 50s, and perfected in the 70s. So we know this very well. Very quickly, the traditional way to do this is you have all these nodes in your graph, and you know the distance between them, or this might not necessarily mean distance. It could represent another value, but you want to shorten along, you want to minimize along that value. And so your algorithm starts at point 1 and goes, well, what's the distance to all of these? OK, the shortest one is 1 to 2. I'll jump there. What's the shortest out of all of these? And so on and so forth. And you can see it sort of filling in as it goes here. Now, this was the original Dijkstra's algorithm that was used in the 50s. However, it was perfected in the 70s by people who said, well, there's no point in actually making this algorithm run on huge distances. Say, for example, you want to visit all the cities in the continental United States. It makes no point for your first step, if you're starting in New York, for your algorithm to compute the distance to Los Angeles, right? Because you know that there are cities that are closer by. And so there's a number of different ways of skipping this. The reason I'm showing you this paper from the 1970s is because, as a pesky millennial, I like to look at these historical things and chuckle. One of the things I love about this paper is that you can immediately talk about the time it was developed in. In the first few paragraphs, they talk about the applications being for telephone networks for many cities, which, to me seems like it's an ethereal concept. I can just pull out my phone and call wherever I want. Or you can look at sort of terminals on a breadboard, right? I tried soldering once and it didn't go very well for me. I burnt my hand quite often. Perhaps what really reinforces the age of this paper, however, is that there's an entire section called storage requirements, which talks about bits and bytes and things. And I carry a 2 terabyte external hard drive in my back pocket sometimes. So it's a nice little look into how far we've come. Here's a schematic representation of what I do with this particular technique. So I start with this distribution of points. Now, these blue points represent groups of galaxies. These are clusterings of galaxies that we've already identified. They're surrounded by these individual galaxies that are perhaps too far from a group, but still form structure. And then finally, there are these more distant galaxies. So at the first pass, if minimal spanning tree is run on these groups, and we identify these predominant high-density filaments, but we continue to see the structure in the void, in the emptier regions, and so we run a second pass minimal spanning tree to identify the structure in those. This is simply so we retain as much data as possible. And then in the third pass, any object that's considered too far from any other structure is considered an isolated void galaxy. And so this gives me 3 products. It tells me which galaxies are in filaments, which galaxies are in voids, and which galaxies are in this interstitial population that I call tendrils. And I can then go back and say, well, what are the other characteristics of these galaxies, and how do they compare? A slightly more complicated overview of this is shown in this flowchart, which I'll talk you through. So this shows a schematic of one of these cones that we have with all the galaxies. And this work that was done by Aaron Robotham et al. In 2011 runs a different clustering algorithm and positions everything in groups. And their central points are shown here. But of course, we have all these ungrouped galaxies, and it would be a shame to throw all this data away. Otherwise, why would we have spent 6 years at a telescope surrounded by kangaroos that were trying to steal our lunch away from us? So all of this data is kept. But what I first do is I generate a minimal spanning tree on these groups, and you can see this skeleton-like structure that's immediately formed. Now you'll see that not everything is joined together. That's because I go through and eliminate links that are too long, because I don't want underdense regions of space to be associated with a filament. I then travel along these links of every single filament, and I scoop all these unassociated, ungrouped galaxies and form this population of galaxies near filaments. So this is one population. These are the galaxies that I can say, these live in very dense environments, these have chaotic backgrounds. I've then got these ungrouped, isolated galaxies, and these form this second population of where I run the minimal spanning tree on them, and they form these tendrils. These are the sort of more loosely grouped objects. And then finally, the isolated galaxies. So these three populations are the ones that I study. Here's how they all look when they're placed on top of each other. And you can see it forms this beautiful cosmic web-like structure. And in the interest of fairness, I've shown here the results from a completely different algorithm that runs on the same data set. And you can see, for this, we have a good agreement in terms of where the voids are. So these are showing my void galaxies in the red regions, which are the voids found by a different algorithm. And you show that they agree quite well. And similarly for the filaments, but there is some contention about what these tendrils are, these sort of interstitial populations of galaxies. And this is an active field where we look at how different algorithms perceive different kinds of structures. And just to go back, here's how it all looks for one particular slice of the universe. And you can see these three regions are all showing the same space, but with different populations of galaxies. And you can see how they all overlap. And here again is this network that's surrounded by galaxies with the empty regions around it. We can actually go in and look at the three-dimensional spacing of all the different points in these. And I show you this figure not just to show you this sort of complicated morphology, but I actually wanted to bring you a three-dimensionally printed, 3D printed copy of one of these. So at NASA, we have the space shop where you can 3D print objects. And so I went to the engineers and I said, hey, can we do this? They said, no, it'll look terrible. I said, do it anyway. They said, OK. Here's what it looked like. I call it a nightmare roller coaster. So what's happening here is that the foundations that the 3D printer is using are looking terrible. You can actually use more sophisticated 3D printers that dissolve that material away, but that costs money. So anyway, the data is there. That's what the data it looks like. And so we can now, in the final few slides, I can tell you about some of the research that I've been doing with this particular data set. Now remember, what do I have in my hand? I have a catalog that tells me the kind of structure that a galaxy belongs in. And other people in the Galaxy Survey have developed catalogs that tell me, for example, the color of the galaxy, how much mass it contains, its shape. All of these parameters tell you about the behavior of the galaxy. So this was a paper we put out last year, and I've summarized it in just 2 figures. So this here on the top right is what we call a galaxy stellar mass function. You can think of this as kind of a galaxy census. What it's showing you along the x-axis is the logarithm of the mass of the galaxy in stellar masses. So this is just the observable mass that we can see. So the higher the number, the more massive the object is, basically. And along the y-axis, I'm showing you the number of objects we see per unit volume of the universe. And so these lines represent, so you can say that at the log 9.5 stellar mass bin, this is the contribution of void galaxies, tendril galaxies, and filament galaxies to the total mass budget of the universe. The first striking thing here is that there are far fewer void galaxies than any other population. That's the first take-home message from this figure. The second and more important take-home message is that void galaxies are much lower mass compared to other objects. So these isolated galaxies are rare, and they're very, very low mass. And as I'll tell you in a minute, the mass of a galaxy is one of the biggest predictors of its overall properties. And so that's what we've shown here in this figure. I apologize for it being cut off towards the edge. And I won't go into exactly what this is showing you, but these are 5 different parameters that tell you about the shape, color, and brightness of the galaxy. And I've plotted here these parameters as a function of the mass of galaxies for all 3 populations. This might seem confusing, but I'm sure you can all appreciate that these lines, these different colored lines that represent the trends in these populations as a function of mass, move in the same way. What does that mean? That means that the predictor for these parameters, such as the luminosity, for example, is not environment, but rather its stellar mass. If it was environment, you'd expect these lines to be different from each other. Perhaps they would have different gradients or be offset from each other. But no, if you simply look at a galaxy based on its environment from this data, you see that the mass is the dominant thing that influences its properties. However, we can see from here that the cosmic web influences the kind of mass budget that a galaxy has available to it. And so that's the final thing that we wanted to study, or the final thing that I wanted to talk to you about, is based on this information, based on our understanding that this mass budget is determined by position along a filament, can we actually observe this? Can we see if a galaxy's position relative to the cosmic web influences its mass? And there are evidence from previous studies that show that this might be the case. Just to focus on these two, this is a paper from 2008 where the observers noticed that in two filaments of galaxies, so these are these lines here, that are collapsing into a supercluster, the fraction of galaxies that are actively forming stars is increased compared to the field. Similarly, another paper showed independently that the fraction of star-forming galaxies in filaments collapsing into clusters is higher than normal. So what does this mean? This implies that galaxies that are falling into these filaments are forming more stars. This then influences their stellar mass, which, as I told you in the previous slide, influences the rest of their properties. So we wanted to model this. We wanted to see if the kind of mass accretion occurs as you travel along the filament, the cylindrical structure, or as you come in along the void for a galaxy that's here. And we actually found that what matters is this cylindrical infall into the galaxy. So we noticed in our results, which I show you here, and this is just a summary plot, where I'm showing the distance cylindrically to the center of the filament and the amount of star formation that is going on in the galaxies. We see a rise in the star formation as a galaxy, a rise in the star formation as a galaxy is towards the periphery of the filament. And that corresponds to a decrease in stellar mass as you go towards the edge. So to summarize, we're seeing in the universe that as galaxies fall into filaments, they begin to form fewer and fewer stars towards the core. But the galaxies that are at the core of a filament typically have higher stellar masses. And so this is direct evidence to show that this cosmic web influences the mass budget of these galaxies. And just to finish, I want to talk about why this might be. So one of the things we often do in astronomy is try and link observational results to theoretical predictions. Traditionally, this happens where a theory paper comes out and the observers rush to try and verify it. In this case, this was a very serendipitous paper by some collaborators who found a few months after we put out our result that they developed this model where you have these what are called multistreaming regions in the universe that are very dynamically complicated. There's a lot of overlap going on in density fields. And as galaxies fall into these multistreaming regions, they experience what are called violent detachments. So they go from being star-forming to detaching from the web and no longer forming stars. And this is precisely what we see in our data. These multistreaming regions correspond to these regions here. So this is a simulation where every column is a step forward in time. And you can see from the field here that you get this sort of initial perturbation, this linear perturbation that's amplified. And it's these regions here where you see a lot of galaxies overlapping on top of each other. And so you expect that the dynamical interactions going on here are very violent. If you'll recall, in one of the earlier simulation videos I showed you, galaxies that were experiencing a large number of these collisions were having their gas stripped away from them. And so if the gas is being stripped away, that could be a reason why the galaxy is no longer forming stars, because that gas is the fuel. And so a final schematic view of this is you've got a galaxy that's forming stars and accreting gas, which is shown here. It falls into this filament and experiences this detachment and then is no longer forming stars. So that's a very elegant theoretical explanation for the kinds of results that we see and sort of is the capstone on this particular result in terms of how the cosmic web influences galaxy evolution. So tying it all together, just to finish, we know now that stellar mass is the most dominant factor that shapes the evolutionary fate of a galaxy. The environment doesn't seem to matter so much once you've accumulated mass. However, it could be, from our recent finding, that a galaxy's position along the cosmic web influences its mass budget and therefore leads to future development. So it's almost a chicken and egg problem, and some of the work that we're doing now is to try and figure out which one happens first. Is a galaxy in a filament because it has more mass, or does a galaxy have more mass because it's in a filament? So just to finish, I want to say that if these kinds of structures interest you, you don't necessarily have to go and get a big expensive telescope and look into space. We have parts around the Earth where we see all these kinds of intricate webs. And I just want to leave up one slide towards the end that shows these kinds of linear structures on the surface of Mars. And one of the things that perhaps we might try and do is see if these kinds of algorithms can be modified to detect these structures automatically. And this is showing you sort of a slightly different alternative use of some of these computational techniques. And that's just what I wanted to leave up here at the end. So thank you for your attention, and I'd be more than happy to take any questions. Thank you.
Thank you for a wonderful talk. I think what was great about that was to get to not only the science, but the hardware and technology behind it, and then the computational elements of it, the data analytics and the use of simulation. So a wonderful bringing together of all of those components.
Thank you.
I also liked that he confessed at the outset that studying something as big and massive as this was just fundamentally cool, which I agree with. I think that's pretty cool.
I can't write that on grant proposals, but I can be honest here.
No. But often we come across this word when we talk about the work of the SETI Institute, and people will say, oh, that's cool. But I think, like your work, it is cool. It's not only cool, though, it's very important and very meaningful. So wonderful talk. And interesting, the scale videos are just fantastic. The scale is so hard to get a handle on. And when we think about, for example, our deepest space probes being sort of at the edge of our solar system or just slightly beyond, what does that mean in terms of how far we've gone? And if the world was the universe and we were on a beach blanket, I guess we'd be at the equivalent of having explored somewhere towards the edge of the blanket so far, maybe not even. But anyway, the scale is impressive. Love to get some questions here, and I'll pass the mic around.
So I got tons of questions, but I'll ask one.
All right.
Have you run, given that we know how star formation works and the galaxy lifespans and things like that, have you run any of these simulations into the future to see like the fate of the universe in terms of these filaments and which galaxies burn out and what happens with that? And does this gas ejected form other galaxies in the void, or what's going to happen there?
So the future is grim. I personally don't run these simulations myself, but we actually know that the peak of the star formation of the history of the universe occurred a long time ago at around Redshift 2, and this is called the cosmic star formation, the star formation noon, or the star formation history noon. So we know now that actually galaxies are beginning to die out. I don't think anybody has specifically run simulations to find where galaxies begin to die off first. However, we now know for example, we were able to use data from our galaxy and mass assembly survey to compute essentially the energy budget of the universe by looking at the total amount of light that's being emitted by this population of galaxies. And you can extrapolate that to sort of account for the entire universe. You can then compare that to the budget further back in time, and we showed that in fact we're losing light. The universe is beginning to die out. Galaxies are no longer forming stars at the rate that they used to, and slowly, gradually, galaxies are beginning to stop forming stars. Personally, I suspect that the first ones to really shut down will be the ones that are in these dense cluster regions because they have been stripped of their gas so much. They're no longer able to accrete the gas because the gas has been violently flung out. It's sort of like if you stir your coffee too much, some of the water is going to spill over, right? And you can no longer bring that back. I mean, you could, be a little gross. But so that gas is lost to the galaxies, and it's probably not going to form new stars again. So I suspect that the first shutting down will happen in these densest regions. That's right, but the kinetic energy that the gas, with which the gas is escaping is greater than the gravitational potential energy of the galaxy, and so it can't fall back in.
When I look at the image of your quenching, where your gas is left behind and the galaxy just goes right through, I cannot help but see a parallel with the bullet cluster images. So what can you deduce of the property of cold dark matter, CDM, when you actually look at these evolution?
So the biggest way in which changing for example, the temperature of dark matter influences these kinds of results is that the coarseness of the filamentary network that you end up detecting changes drastically. So for those that might not be so familiar with this in the audience, if you vary the temperature of dark matter, you change the complexity of the structures that I was showing. So rather than seeing these sort of very splintered filaments, you begin to see ones that are a bit more coherent. And so this is just a hunch, but I wonder perhaps if the temperature of the dark matter is lower and you see fewer of these coherent structures, that perhaps the density field that these galaxies might inhabit might be less complicated, and it might have some impact on the star formation, but I can't give you a definitive answer.
I've got a question about this granulization, and it would appear that the entropy of what you see is decreasing. That's got to be compensated for in some ways, that the gas between these structures, or I mean, obviously it has to increase ultimately at some point.
Well, I think it comes back down to this this gas ejection and the dynamical interactions that are having. So you have this net loss of, all this dynamical gravitational energy is transferred into this gas that's flung out. And by the same token, all of these stars that are taking the energy in the gas and forming that into, through nuclear fusion that are forming stars, they're just dissipating that heat. Of course, one of the ways in which entropy causes this dissipation of energy is through radiation of heat. So we're kind of seeing that on a cosmic scale. And again, going back to the idea of the gas, you have all this gas being flung out. So the universe is becoming more complicated.
Hi, thanks for the great talk and the explanation of why those wings are missing in the large-scale surveys that we do. But that sort of brought up the question, since infrared light permeates the interstellar medium, and a recessional velocity of only half the speed of light would be redshift 0.7 or so, why don't we have, why are the wings all the way out instead of just up and close? Why can't we see past? Is that an instrumentation problem?
It's an instrumentation problem in the sense that, so the reason they fan out is simply because of the perspective. It's if you held sort of a bar in front of your eyesight and moved it further out, it would occupy less space. So because the bar of the Milky Way is so much closer in compared to these other distances, it occupies a large fraction of space. The problem is that the dust is simply too dense, and so no amount of light is able to penetrate. So we simply can't get that information through the dust, because if it were perhaps only one layer of dust that was being warmed, you might be able to conceive of some way that you could reconstruct the background galaxy distribution from that single emission. But you have so much of this intervening material that the signal is simply lost. So what we really need is some science fiction solution to the problem where we send a probe above or below the scale disk of the Milky Way. But that's, I think, a problem for many future generations.
This is more of an art question.
Okay.
Can you consider the universe, if there was such thing as simultaneity, since we're looking back in time, can you have like a time equals 0 where there is no time? What would these structures look like if, 14 billion years ago, where are they now compared to our local time?
That's a difficult question, and I don't think I'll have a satisfactory answer to you. The simulations, I think, give us the best way of seeing how these structures evolve, how we go from this soupy distribution to a much more discrete one. But to take your question back to the studies that we do, one of the most common problems in astronomy is to look at galaxies that we see in the universe today and sort of look for their progenitors, right? Because you can't take this distribution and sort of rewind it back in time. You can't look at a galaxy and track where it came from. So often we have to observe galaxies at different distance bins and to try and match them up. So it is a problem, and I think in terms of going back to what you asked, what it looks like, I think we have to rely on simulations to be able to do that. Yes, so the further back you look, the properties of the galaxies that you see are different. So for example, as I was saying, we had this era in the universe at redshift about 2 where there was a lot more star formation going on. So you can go back to that era and see these galaxies that are forming a lot more stars that are a lot more luminous compared to the ones now.
All right, any more questions?
Yes, you're studying what I guess you call it low redshift, although low redshift, I mean, high redshift is like 2.
Yeah.
But at that point, is dark energy a factor you have to put into your calculations, which would be pulling things apart and slowing down formation?
At higher redshifts, that's certainly something that you have to take into consideration. But we simply don't have enough data, observational data at the distance scales where that kicks in to require that kind of correction.
All right, any more questions? I think we have time for another one.
So at the beginning, you mentioned sort of looking at dark energy or alternative models for gravity, and I'm wondering how your algorithms are used to test some of those different models.
Thanks. So personally, my algorithms aren't. So especially as you finely vary the nature of gravity or dark energy, the resulting changes in large-scale structure are perhaps too fine for algorithms such as this to detect differences. More commonly used techniques are, for example, the power spectrum, where you look at the power spectrum in the cosmic microwave background radiation. Or you can look at things like the 2-point correlation function, which is kind of, in a very simplified sense, it's sort of a histogram that shows you the pairwise distances between objects. And it's more these global statistics of distributions of galaxies, either spatially or in angles, that vary as you inject different kinds of physics that are going on. Unfortunately, the work that I do isn't sensitive enough to detect that. But there's a lot of work going on in terms of running simulations with different physics, and then deriving these summary statistics from the final resulting distribution and comparing it to what we see today.
Very good. Well, I'd like to thank you once again. I think this is the moment where we do the traditional handing of the prized SETI Talk Speakers coffee mugs.
All right.
So, without further ado,
thank you very much.
Thank you again. It was a wonderful talk.
Thank you. Thank you. Thanks.
Thanks again to all of you, and especially to those of you who, for whom this was a first-time experience. We hope you'll come back for more. We hope you'll visit our website and get to know us a little bit better, and also consider supporting our quest. It helps us bring this wonderful series to you. Thanks again very much, and have a wonderful day, and happy Thanksgiving.